Hello, Mr. Simpson here with our first video for Chapter 10, 10.1 Intermolecular Forces. As always, the learning objectives are listed here. Please pause the video for a moment and write those in your notes. In order to truly understand intermolecular forces, it involves basically three steps, and you can see those outlined in the learning objectives here. First, understanding what in general intermolecular forces are, and then specifically what are the different types of forces are and how they behave. Next, be able to identify which forces are present in different types of molecules. And finally, how do the relative strength of those forces affect changes of state, so going from a liquid to a gas. So let's start with a basic understanding of intermolecular forces. These are the forces of attraction that exist between atoms and molecules. So if you think of bonds between atoms in a compound or molecule, those would be intramolecular forces. Intermolecular forces are forces of attraction between those molecules and atoms. So these are not going to be as strong as the intramolecular forces that hold atoms together inside the molecules. Okay, this has to do with differences in electrostatics, so forces of attraction between positives and negatives. We talked a little bit about unequal sharing and partial positive and partial negatives, whether it's in bonds or molecules. So those differences in forces will cause these intermolecular forces of attraction. It requires, in order to overcome the intermolecular forces, it requires energy. So kinetic energy is the type of energy provided that will break the intermolecular forces. So, and we are familiar with kinetic energy in terms of heat and temperature. So as heat is added and temperature increases, intermolecular forces are broken. And if intermolecular forces are broken, substances can change state. Here's an example of what we're talking about here. So you can see going from solid, liquid to gas, that you're increasing kinetic energy or temperature as you go across. So as I increase heat, the intermolecular forces are broken. Okay, so I've got lots of intermolecular forces and strong intermolecular forces when I have a solid, and then some of those are broken. So now I have fewer intermolecular forces, and my molecules get to move around a little bit, and then more intermolecular forces are broken, and now there's freedom of movement in the gaseous state. Okay, so the types of intermolecular forces are listed here. And one of our goals as we go through these, I'm going to go through and explain each of them in some detail. And then one of our goals is to also understand kind of how we rank these in order of weakest to strongest. Okay, so I'll be coming back to that at some point as well. Sometimes you see this term van der Waals forces. So that is just another way to refer to the intermolecular forces collectively. So sometimes you'll see it listed as van der Waals forces. Let's start with dipole-dipole attractions. So we know that polar molecules have regions of partial charge. So as you can see here, we get a partial negative charge and a partial positive charge, and that is a dipole. Okay, so if you remember thinking about drawing that dipole moment here, from the partially positive end to the partially negative end. And then this is going to obviously be attracted to the partially negative end will be attracted to partially positive regions in a nearby polar molecule. So if I have a polar substance, then I'm not just going to have one molecule of it. I'm going to have numerous molecules, and all those molecules would be attracted by this dipole-dipole attraction. In order to identify that a dipole-dipole attraction is present, I would need to be able to draw a Lewis structure and then identify that I have a polar molecule. Remember, the quickest way to identify a polar molecule is if there's a lone pair of electrons around the central atom. Next are the London dispersion forces. Okay, so a couple key points here. So all substances have London dispersion forces. Okay, some substances are going to have multiple types of intermolecular forces, but off the top, you can say that and everything's going to have London dispersion forces. And the reason being is because it has to do with a distortion of electrons. So it has to do with the movement of electrons in a molecule or atom. This motion of electrons creates what's known as an instantaneous dipole. Okay, an instantaneous dipole. So if I think about, our positive nucleus and our electrons, whether it's an atom or, in this electron cloud. So because these electrons are moving, it's reasonable to think that, at any given point in time, maybe I get a situation where I get an electron density with a lot of electrons over here to one side of the molecular atom. And if that happens, you can see what would happen is we get that partial negative region and that partial positive region. We get that dipole. But it's not going to stay like that. Those electrons are going to reconfigure and balance back out. So that's why we refer to it as an instantaneous dipole. Well, if there's an instantaneous dipole happening here in this atom or molecule, then what I would expect to happen, or what could potentially happen, is we could get an induced dipole in a nearby atom, right? So if all of a sudden if this atom or molecule gained this partial positive, well, then that's going to attract more electrons in a neighboring atom or molecule. And again, we get this region of negative and region of positive, and we get this dipole interaction. But again, this is not going to last long. It's an instantaneous dipole, and it's going to kind of reestablish and go away. So for that reason, London dispersion forces, or LDFs, or sometimes just dispersion forces, are the weakest of the three forces. Okay, they are the weakest. The other thing to think about here is that heavier molecules have stronger dispersion forces. Okay, so basically, how large a molecule is, it would have more electrons, and those more electrons would be further from the nucleus, so you would get a greater polarizability. And then, so if that's the case, then your London dispersion forces, that instantaneous dipole, may happen more frequently, and it also may be stronger because of the number of charge involved. So you get London dispersion forces do get stronger as we add size, more energy levels, and more electrons to our atoms and molecules. Here's an example of changes in London dispersion forces over time in the same family, right? So carbon and hydrogen, silicon and hydrogen, and so forth in that same group, you can see that the temperature is increasing pretty significantly as the size of our molecule or the number of electrons present increases. Okay, so this would clearly be the smallest. So London dispersion forces are weak to begin with, and then these are weak in comparison. But as my atoms get bigger, my molecules get larger, and I have more electrons in the mix, you can see what happens is I still do get an increasing in boiling point temperature there, because it's going to be harder to break those London dispersion forces. Okay, the last type of intermolecular force is hydrogen bonding. This comes from, first of all, this only happens when we have a hydrogen bonded to an oxygen, a hydrogen bonded to a nitrogen, or a hydrogen bonded to a fluorine. So in those three circumstances, hydrogen bonding is present. So obviously a common one here would be water. So oxygen is more electronegative than the hydrogen, and hydrogen enters into this covalent bond looking to get two electrons. Well, because oxygen is so much more electronegative, it's going to pull that shared pair closer to itself. Hydrogen then, in search of that lone pair, that pair of electrons, will then have a force of attraction to a lone pair of electrons in a nearby molecule. It's a bad name, hydrogen bonding. It is not a bond. It is still an intermolecular force. But the reason why it happens in these three examples is because Those are oxygen, nitrogen, and fluorine are very electronegative, and they're also small, so that strength would be the greatest. So hydrogen bonding represents the strongest intermolecular force. So it goes hydrogen bonding is stronger than dipole-dipole, which is greater than London dispersion forces. So those are our three types of intermolecular forces and their order of relative strength. Here's a little better picture of the hydrogen bonding that occurs in water. So you can see the hydrogens here in multiple molecules being attracted to those lone pairs that are sitting on the oxygens in each water molecule. So the relative strength of intermolecular forces are going to affect changes in state, because in order to go from a liquid to a gas, in this case we see this on the boiling point graph, intermolecular forces have to be broken. Okay, so you can see in a particular family here that intermolecular forces change dramatically when we add hydrogen bonding into the mix. So H2O, HF, and an H3. And then from there, they start to change, as we saw from an earlier graph. They will increase, but more gradually, as London dispersion forces would get stronger because our molecules are getting larger, more electrons in the mix here. So that wraps up our introduction to intermolecular forces here. Now we want to be able to apply this to properties in the last learning outcome to properties like boiling point and melting point. So if, for example, I had H2, Br2, H2S, and H2O, and we're asked to put these in order of increasing boiling point, well, then what I would do here is think about what intermolecular forces are present. So in the case of H2, this would just be London dispersion forces. Same here. Those are do not have a hydrogen bonding scenario, and they are non-polar molecules. H2S, also everything has London dispersion, but this would also have dipole-dipole interactions because H2S is a polar molecule. You would have that bent arrangement there. So lone pairs around the central atom is my quickest clue that I have a polar molecule. And then my oxygen, I'm going to have the hydrogen bonding. So I will have LDF, I will also have dipole-dipole, and I will also have hydrogen bonding. So if I was asked to put these three things in order of increasing boiling point, let's say, H2O would clearly have the highest boiling point. H2S would be next. Okay, so now H2 and Br2 both only have LDF. You may be tempted to say, well, they would be the same, but Br2 is larger, has more electrons than H2, so it would have a higher boiling point. That wraps up our first video for Chapter 1.